Welcome back, and this is going to be our final example video on implicit differentiation. So, now we have the task of finding a second derivative. We haven't found a second derivative so far, and there's actually something interesting that happens. So the first derivative is kind of lame, okay? We can find the derivative by, again, applying the, the differentiation operator with respect to x to both sides. So we would end up with 4x cubed, plus 4x, or 4y to the third times dy dx. And then this would just equal 0. Okay, and we could find dy dx per normal. Divided over dy dx is going to equal negative x cubed over y cubed. Okay, that wasn't such a challenging task. Okay, and if we want, we can also say that that's y prime. But we need to find y double prime. So what do we need to do? We need to differentiate this again. So we want to find dy squared over dx squared, which is the same as y double prime. So we need to differentiate this. Well, that's a quotient, so we need to do the quotient rule. Okay, quotient rule says I need to do low, and then d high, I'm going to chunk the minus with the x, so d high, so minus 3x squared, dx dx, okay, and then minus high, d low, okay, so now 3y squared times the derivative of y, so dy dx, all over low squared. Okay, now you'd think you'd be done at this point, right? Actually not, right? Because you have this dy dx expression there. What do you do with that? Well, don't we find dy dx? Isn't it like right there? So we need to substitute this back in and see what we get. Okay, so simplifying this, we get minus 3x squared y cubed plus 3x cubed y squared times, now I'm going to insert dy dx, minus x cubed over y cubed, and then all over y to the sixth. Okay, and for us, this doesn't seem like it's too terrible to simplify. If you end up simplifying it, I'll just do some dots here. You end up getting let's see, I forgot the minus sign out in front in the numerator over here, but you would end up with minus 3x squared y to the fourth. Hang on, I know that you're wondering where the fourth come from. X sixth over y to the seventh. So when you simplify this, this would be left with a y in the denominator over here, and then we just increase the power on y in both of the other terms to account for that. So this is what it would simplify to. Oh, and that should actually be a minus. Okay, so big idea here is if you're finding a second derivative that uses implicit differentiation, make sure to substitute in the first derivative that you already found and simplify. Okay. Last thing, remember that we talked about parameterized functions a little bit, but also there's this idea of orthogonality, and that idea of orthogonal curves came up a little bit in there, but when we talk about orthogonal curves, that means that they're tangent lines. If we have two functions, they would be perpendicular at each point of intersection. Okay, so for this one, we have these two kind of classes of functions. We have to determine c and k. I should also say orthogonal at the point 1, 1. But we need to find these values. Okay, so for this one, this first one, we could say dy dx is equal to 2cx, right? And for the second one, we could go through and find its derivative as well using implicit differentiation this time. So 2x plus 4y dy dx. And if you solve, is equal to 0. And if you solve that for dy dx, you end up getting negative x over 2y. Okay, and so when we think about them being perpendicular, we remember that if we have a slope or we would have two slopes that when we multiply them, they would be -1. Okay, and also another way of saying that is that one is the negative reciprocal of the other. But if we look at their slopes and multiply them, so there's slope 1, here's slope 2, we want that product at 1, 1 to be -1. Okay, so let's plug this in. Put in the point 1, or put in the values 1 and 1 for x and y. We get 2c times -1 half. Oops, I forgot the 2 here. -1, or times 1 half is equal to -1. And so then we can go through and c would just be -1. I'm sorry, +1. So this gives you that c is +1. You might note here, this is the only condition that we really need, right? We need c to be 1 in order for these two curves to be orthogonal at 1, 1. K, it actually doesn't much matter. So you can check this using Desmos, but for any k, this should be, so k I'm just going to say is a real number. K can be anything. All right, so you can check this using Desmos or another graphing utility. Does it look perpendicular by inspection? But here we've gone through and algebraically shown that for this particular value of c and any value of k, they're going to be orthogonal. Okay, so again, just another little application of implicit differentiation here, and I think we should be good to go and ready for a workshop. So I'll see you then.